Hello there. We are on our fourth queuing tutorial. Not our fourth video, but our fourth queuing tutorial as far as the documentation is concerned. So in this example, we're going to look at expanding our idea now of not only having a network that different individuals or customers or whatever flow through, but now we're going to expand it such that there are also different types of customers or different types of things that flow. I think this one's a healthcare patient example. So we're going to go through the documentation example together. And I believe after this, we will move from tutorials into following the guides in the documentation. But let's finish this one up. So, the tutorial, multiple classes of customers. Imagine a 24-hour pediatrician's clinic. So it is a healthcare example. And we have two different types of patients. We have babies and we have children. When patients arrive, they must register at the reception desk. So that itself may be one of the nodes in the network. We'll see. Registration time is random. In other words, it's a random variable, but we'll see what they decide for probability distributions in this case. So, but for babies, lasts an average of 15 minutes, and for children, an average of 10 minutes. After registration, the two types of patients go to separate waiting rooms where they wait to be seen by separate specialists. Appointments with specialists take a random amount of time, but on average last 1 hour. Okay, so they're telling us the average, but they're also telling us it's random. That makes sense. There is one receptionist on duty, so that's the number of servers. Two baby specialists on duty. That's another. So that's the number. The first number there, one, for one receptionist is for the receptionist desk. The two baby specialists on duty are for serving the babies, and three children's specialists are on duty. Great. So babies arrive randomly at a rate of 1 per hour. Children at a rate of 2 per hour. In this setup, we have a scenario where two different types of customers are accessing the same resource, but may use them in different ways. Q handles this by assigning customer classes to customers, labels with strings. And in this example, we're going to have one for baby and one for child. And then we have a 3-node system of the receptionist's desk that gets utilized by both babies and children, so to speak, although I'm sure that when it's a baby, the baby is probably not the one doing the talking. And we've got a children's specialist for node 3, so a 3-node network. Okay. We assign different behavior for different customer classes by replacing the values of the keywords of the network objects with dictionaries, going from list to dictionaries, okay, with customer classes as keys and the required behavior as values. Okay. So this is probably reasonable for when you can always define like a finite collection of patient types. I think that well, I'll show you in the future, I hope, some ways of having different attributes that make for different types of patient or customer on like a continuous scale. But this is the easiest thing up front when you have like a finite collection of buckets, is to have these predefined classes. So we're going to type out their example and talk through it. So let's make tutorial number 4. As always, import the Q package first, because that's the package we're working with. We need to import it, and we'll define our network to be using the constructor again. And from there, let's start defining arrival distributions. So now it is a dictionary instead of a list. And we need to specify what these different... We need to specify basically all the same information now, not just on a node-by-node basis, but also by a customer-class-by-customer-class basis. So for each customer class, we'll define what happens to them at each node. So we got Q dists exponential, and that's a rate of 1.0. Remember, this is the arrival distribution. So that is to say that the inter-arrival times of babies at the node 1, which was the reception desk, follows an exponential distribution. It's a stationary exponential inter-arrival time distribution. So some of you may also know that that is going to give us, for some interval of time, a Poisson distribution number of baby arrivals. And there are no arrivals of babies at either the children or children's service or the baby service, right? They all come through the receptionist desk first. So that's it for baby. Pull those in. And then let's do child. I assume that the exact string match needs to be correct. Like if I did small case child, I don't think that that would work unless I did it as small case child for all of the buckets, all of the classes. So let's go Q. Dists will also follow an exponential distribution, and all that theoretical stuff will also apply there. And we'll go none and none, and then close that off. We have the end of our dictionary there. Let's put a comma to say, let's move on to the next argument. So we've defined the arrival distribution, inter-arrival time distributions for babies, that at the reception desk, they follow an exponential of with a rate of 1, and the children arrive at a higher rate of 2. Okay, and then that's it for arrivals. Let's go on to the service distributions. Oh, not service disciplines, that's also an important topic, which we will get to in the future. So again, dictionaries instead of lists. And let's define the service time distributions for babies at each node. So at the first node, that's the receptionist desk, will follow an exponential with a rate of 4.0. And the baby service is going to be distributions exponential 1.0. And then for the last node, Q, dists.deterministic value equals 0. Now, you probably have some choices here. This is, I'm not sure what formal term I would use here, but here's the thing about this last node. The last node actually isn't for babies, it's for children, right? And so they shouldn't arrive there in the first place because of how we're going to set up the routing, but the tool doesn't know that. And so you need some kind of placeholder. I, off the top of my head, do not know what the best choice is. You might also be able to put none here or infinity float something. I think you could do different things, but it doesn't entirely matter here. And that if you're coding this up, you might want to say some kind of comment or warning. Not used, something like that, because we're not going to use it. Okay, and then we can move on to child. And for them, they have at the receptionist desk, dists exponential and a rate of 6.0. Yes, and q.dists. And so we have the same issue going on with children at the second node. You shouldn't ever have children at the second node. They are only for babies. And so you could put all kinds of things here, and that distribution should never get used. However, when they're getting served by the specialists for children, it happens at a rate of 1 following an exponential distribution. Okay, so we've defined the arrival distributions at each node, and we've defined the service distributions at each node. That. Okay, so what's next? We'll define the routing next. Now, the routing is not any different than any of these other parameters. We need to specify it for every class. Now, it's using the customer classes is kind of an all or nothing thing. You have to specify it everywhere or nowhere. And so here's where we're specifying it everywhere. At least last time I experimented with that. Maybe I'm wrong, since the package does get updated over time, but last I checked, that was the case. So 0.0. So what does this mean? When we're at the first node, the babies have 100% probability of going from the receptionist desk to the baby specialist. Okay, yeah, it's going to complain about a bunch of errors, but that's okay here. So the baby, once it's leaving the second node, will basically go nowhere except for leave the network entirely. It won't go to any of the other nodes within the system. So that's a probability of 0 for each of the 3 nodes we're talking about. And then What am I doing here? Oh my goodness. There's this silly thing with NeoVim in caps lock. And I accidentally turn on caps lock quite a lot. Okay. Oh, actually, yeah, no, that's fine. We'll just redo that. Times 3. And also the same thing for the last node as well, times 3. Is that right? We got 0, 1, 0, row of zeros, row of zeros. It's good to double check some of these kinds of things. Maybe I'll put another bracket there just to be clear. Okay, so we should be on to the child now. And the first row is going to be 0. So if you're a child arriving at the receptionist desk, you won't go back to the receptionist desk. You will move on. And then there's a 0 chance of a child going to the baby specialized service, and there's a 100% chance that they go to the child specialized service. Then there's it kind of doesn't matter too much for the child here that the child will never go to the second node. So you can put all kinds of things here, and it should be observationally equivalent, even in your simulation, not just in reality. And I guess I decided to type all those out, which is fine. Close up that list. So that's our state transition matrix, our routing matrix, sorry, which is a form of state transition matrix of a sort. And I guess we need to also close off that dictionary. So those are our 2 routing matrices. Looking at it now, it's not formatted very nicely, but you know what? I am really not gonna worry too much about it. And next, last but not least, one might say, we are going to define the number of servers. And in the description, it told us that there's 1, 2, and 3. So that's, again, 1 receptionist, 2 specialists for taking care of babies, and 3 specialists for children that are, non-babies. Okay. Let's just do a quick little check that this actually doesn't give an error. It doesn't, so at least it's formatted correctly up to the semantics of this API. Now let's get back to the documentation and let's do a little bit of an update. This is one of the things where, we're running full steam ahead through the definition and could read this more carefully and explain it in more detail, but I think that we're mostly good there. So notice that where we want to know certain customer classes will not require a service. For example, babies will never require service at the children's specialist, so class 0 customers will never require service at node 3. We are still required to input a service distribution. We choose the dummy distribution to be the deterministic with 0 for the value, so that's fine. And then they get into doing simulation, so let's do the same. Let's go down here. And actually, let's make ourselves a bunch more space. And let's define a simulation object, simulation. We'll pass in our network model into it. And then we'll do simulation, simulate till max time. And we'll simulate only for 9 units of time, which in this case is hours. So one of the things hopefully you're noticing across these tutorials, if you're watching multiple of them, is that you can make this assumption, but it's an implicit assumption about the units of time that you're going to use. It's probably something worth documenting when you're setting up a simulation, is to say what unit of time you're using. And we'll get all of the records. And that still runs, so the simulation doesn't have any internal issues. So what is the next part in our tutorial? Now we should see that no baby ever reach node 3 and no child ever reach node 2. So here they're doing some validation of the claims that we were just talking about in terms of those dummies. So visited by babies equals a set of 1 and 2. Those are just the nodes they're allowed to go to. And we could also do visited by children or child. I guess we'll use full words there. And this is 1 and 3 rather than 1 and 2. Now they've got quite an involved list comprehension here. Let's start by breaking apart the... They're going to return a set because they're not interested in every multi-set value or every like time that they went to each node. We just want to know, is the set of nodes visited by babies the same as the set that we just defined above? So we can go r.node. R here is an abbreviation for record. So r.node for r in recs or records. If r.customer class, so this is the first time we've accessed that variable for taking a look at details about which customer classes we've got. It's the first time we've done that, and we can check, is that visited by babies? What have I got here? It's probably an expression not used issue. And true. Great. Let's do the same, but for children. Both true, just like in the tutorial. Well, that's good. That's a nice little sanity check, and actually, come to think about it, if you're working on really complicated models where the model itself is becoming very hard to reason about purely because of its size, it makes sense to start putting in extra checks for things, even if it's just for debugging purposes. So if I was just going to do, for debugging purposes, I want to have an assertion that that set is the same. I could put those in. I could also raise them as errors. That you may want to do some validation on your simulation results just to make sure that you did the simulation that you think you did, that you think you defined. Okay, what's next? Now, say we'd like to find the average waiting time at the reception, baby specialists clinic, and children's specialists clinic. We'll simulate for 24 hours using 3-hour warm-up and 3-hour cool-down for 16 trials. Let's collect the average wait times for each class at each node every time. Now here are some pretty long list comprehensions going on here. And that's where, honestly, if I was writing up some simulation, I'd probably write a class or a function to take care of extracting what I want so that I don't have such a hefty thing to look at here just in terms of the, for trial run simulation kind of loop. I'd write some kind of like extract results kind of function. But we're going to try to follow the tutorial. I may have to, just because those list comprehensions are so long, jump back and forth a little bit in the view. So let's do it. I think we could keep that there, but maybe I'll just comment it out. So let's go for trial in range, and we said there's 16 trials. We could define this as like a larger parameter, num trials equals 16. We'll indent that stuff. We're going to want to set seeds. So let's go q seed, and we'll just set it to the trial number. And then, sure, we'll initialize a simulation object using the same network, and we will simulate until a maximum time of 30. I think if I was being really well organized here, I'd probably split this into the different waiting time, or warm-up time, cool-up time, and whatever you want to call like the target interval time. But I think I'll just leave it for now. We'll follow the tutorial. And let's go recs and go sim dot. Oh wait, no, we already got that one. Sorry. Typing things out. All right, let's get into these long list comprehensions. I have to say I'd probably do this as like a dictionary comprehension or something else that's just like grabbing by class, but that's fine. Waiting time for, and actually let's break this out into a bigger format since it's a pretty involved list comprehension here. For recs, if r.node equals 1 and what? So this is getting annoyingly involved. It's one of the things I really wish there was word wrap on the docs. Hint, hint to folks that develop Q. So what should we do here? I think I'm just gonna actually just copy paste this, and we'll format it together and talk about what's in here. What's the longest one I can't read? I can't actually read pretty much all of them except for the bottom two. So we're just gonna copy paste our homework because I don't feel like typing all that stuff out and swapping back and forth between what we're looking at. Oh, lazy. Okay. So let's clean up these and talk about them. We're going to grab the waiting times at node 1 for babies. That's what this is for. And so we're going to grab the waiting time, and we're going to grab the waiting time for each record in the records if the node is the first node and the arrival date is past the warm-up time, which is 3, and it's less than the time that we start the cooldown time, which is 27. And it has to be for babies, right? Because we're looking at weights 1 babies. Okay, so then we want to get the next one, which is the waiting times at node 1 for the children. So that's the receptionist. Just recall what we're actually grabbing. So we grab the waiting time for record in records if the node is the first node, and if the arrival date is past the warm-up period, which is 3, and if it's before the cooldown period starts, which is going to be 27, and we'll ensure that we're filtering down to the customers that are children. Woo! Okay, a couple more to go. So the waiting times at node 2, which we've dropped the is it a baby or a children here because we know that node 2 only serves babies. But if we wanted to expand that out to a model that has both, we might want to look at both. So our record waiting time for each record in records, we're going to filter down to the cases where the node number was equal to 2 and the arrival date was past the warm-up period of 3 and was before when the cooldown period starts at 27. And last, we get weights 3, which is the waiting times at node 3. Again, we haven't specified whether it's baby or child because only children get served at node 3. So we got our waiting time for record and records if node is equal to 3 and the arrival date is no sooner than when the waiting time has ended and is no later than when the cooldown period has ended. And okay, and then this is just aggregating or appending some results. So we actually didn't write those lists, but we can write them up here. So we got average weights 1 babies. We'll make that a list. And let's also grab that and call that for children. And then we'll have average weights at node 2, which is only for babies, and average weights for node 3, which is only for children. Okay, and we're also missing the last couple of appending to waiting lists, which we can do ourselves here just because I can see it and I won't be quite as annoyed about having to deal with word wrap issues. Weights 2. So we're really just appending, we're calculating and appending the average. So that's the average part is the sum over the number of numbers that we're summing together. Okay, and we'll do that again for node 3. Thought this was going to be a shorter video, but look at me just typing. Very fastidious. Okay. Right. Should be good. Oh, I guess I could have done that, but no, that's fine. That is fine. Now, they want us to print out some of the average of the averages. Maybe I'll do that down below here. We'll leave this stuff. I mean, imagine that you had just done all the simulation and you want to do quality control checks to make sure it's still correct and all that. But here, let's just jump into our average of averages. We'll print the sum of the average weights 1 for babies and divide that by the length of the average weights 1 for babies. And then we also have one for children and another one for children. Then we'll get to the waiting times for node 2. So we'll do the sum of the average weights 2 divided by the length. There's nothing that makes me more excited in life than just calculating averages. I kid. No, the averages actually can be a reasonable measure of roughly where the center of the data values are. It's not necessarily the median or the mode or anything like that, but for many distributions that are roughly unimodal and not too horribly asymmetric, that, yeah, it gives you something that's kind of close to the mode. Or maybe you do want to think about it kind of as like a center of mass, which doesn't have to be the mode at all, right? Anyway, okay, so let's do that last one there. Average weights 3. We'll take that sum and we'll take the length of the average weights for 3 and print. And oh my golly gosh, we will print the results. And I didn't have any typos, at least nothing that broke anything. How do our numbers compare to theirs? 0.29. 8, 4, that looks good. Second one looks pretty good. Same with the third one and the fourth one. Okay, so I think we succeeded at reproducing their calculations there. Now, what does the last little piece say here? These results imply on average baby's weight we'll call it 3 plus 0.27 is approximately equal to 0.567 an hour, around 34 minutes for an appointment. This could then be used as a baseline measure against which to compare potential reconfigurations of the clinic. Yeah, fair point. If you're doing facility planning and you're trying to figure out how the facility itself should be organized, that's one of the more subtle things that is not about even changing how many servers you have or employees providing service. Sometimes you need to just reorganize how patients are routed through the system. And by the way, like, why again, since we're at the end of the example, why again did we think that this was some kind of useful computational thing to look at is that if I ran a single queuing system with just babies, I'd get one answer. But that answer with the same arrival rates and service times would still give me a different throughput, just because at the front desk, the arrivals of children is interfering indirectly. Sometimes babies may have to wait for children and vice versa, where if they were completely independent flows of patients, that you wouldn't have that. They'd get a different effective higher rate. So that is sort of in its own way, well, there's, I'm sure in the end, trade-offs in real systems. One of the rules of thumb to look for is, can you split things apart more to increase the rates? Okay, so with that, thanks for watching this video. Hopefully you got some value out of looking at the multi-class setting of queuing networks, and I will catch you in the next video. Take care.